Hi everyone, my name is Matt Layher, and this is how to export Prometheus metrics from just about anything. Just to start, here's a little bit about me. I'm a senior engineer at DigitalOcean. I'm a member of the Prometheus team. You can find me on GitHub and Twitter at MDLayher, and all of the content available in this talk will be linked to from this repository here, my talks repo on GitHub. So just to start, let's talk about a crash course on Prometheus. So how many folks here have deployed Prometheus in their environments? Quite a few. That's awesome. That's really great. So what is Prometheus anyway? Prometheus is an open source systems monitoring and alerting toolkit. It uses a pull-based metrics gathering system over HTTP and a simple text-based format for actually exposing those metrics to a Prometheus server over the network. It also features PrometheusQL, which is a powerful query language built right into Prometheus. The Prometheus architecture looks a little something like this, but for the purposes of our talk, all we really care about is the Prometheus server in the middle, a display such as Grafana on the right, and jobs and exporters and other sources of pull-based metrics on the left. This is an example of the Prometheus text format. So if I curl the node exporter running on my local machine, we'll see a little bit of information about metrics here. So a metric has components such as a name, possibly some labels that describe different dimensions of the metric, a value, which is a raw float64 value, and some metadata, including help text that helps you identify what a metric's purpose is, and also the type, such as counter, gauge, summary, or histogram. This is a super basic example of PrometheusQL, so I just say, Prometheus, give me the value of this time series from this instance over the course of, let's say, a 24-hour period. And this shows the hard drive temperatures on some of the machines at my house. So what is a Prometheus exporter anyway? An exporter is a system that bridges the gap between Prometheus and systems that do not speak the Prometheus metrics format. So you might have some service that exposes metrics to something like statsd, or perhaps it has like its own custom JSON endpoint or xvar from Go. But sometimes those systems aren't compatible with Prometheus, so that's where exporters come in. And typically, you would run these on the same machine as the service itself, but not always, as we'll talk about later. So some examples of some extremely common exporters include the node exporter, which exposes system metrics from Unix-like machines, such as Linux and FreeBSD. The MySQLD exporter exposes metrics from a MySQL server, and the black box exporter. And this is a unique one. It actually dials out to remote systems using things like HTTP or ICMP ping to probe these black box systems. So let's imagine a world with a cloud-native future. You've got your Prometheus and you've got your cloud. And the cloud's up. It exposes a metric that says everything's all good, right? So who has an environment that looks something like this? Oh, nobody. I was going to ask if I could come work with you, but some of us live in a bare metal reality. We've got all of these switches and core routers and spine switches and top of rack switches. And we've got these racks upon racks of bare metal servers. So naturally, I log into the router and I say, please give me Prometheus metrics. Seems like a very polite thing you would ask a router. Oh, no such luck. What gives? Okay, so Linux is pretty open source friendly, so there's probably like a Prometheus metrics device file, right? Oh, no such luck. So where can I find Prometheus metrics for these systems? If you want to find Prometheus exporters, your best bet is the Prometheus website, or you can scour the internet, the mailing lists, the Prometheus wiki on GitHub, and etc. Or as a last resort, you may just have to roll your own. And that's going to be the focus of our talk today. So let's start with some of the basics of building an exporter in the Go programming language. So to start, your function main is going to build your types, wire up dependencies, and start an HTTP server. So first, we create this collector type we'll talk about shortly, and we make the Prometheus client aware of the collector. We set up an HTTP handler and expose metrics over the standard /metrics endpoint, and then we finally start listening for HTTP connections for Prometheus. So let's talk about the Prometheus Go client a little bit. The most important interface is probably the Prometheus collector interface. And Prometheus client uses this to actually expose metrics over the network. So our collector structure here is going to be our implementation of the Prometheus collector interface for some service. And let's say we want to expose a metric called requests total, which is just the number of requests that go to some arbitrary system. And also, we're going to explicitly pass a function dependency here so that we can swap this out for testing. But this function is going to return an integer, that is the number of requests that have occurred, and an error if anything goes wrong. Okay, so let's create our collector. We have this constructor here. We explicitly pass our dependencies, makes things much easier to test, such as our request function, so we can swap it out. And also, this is where we actually create the meat of our metrics. So we have our request total metric here. We give it a name, such as exporter request total, a help text, such as the total number of requests that occur, meant for humans, and also if we want some label dimensions. But in this particular case, we don't need any variable or constant label dimensions, so we go ahead and omit those. So the first method of the Prometheus collector interface is describe. And describe accepts a channel of metrics, or a channel of metrics descriptions, excuse me, and then it gathers metadata about each metric. So basically, you can collect them in a slice and iterate over that, pass the descriptions on the channel, and you're pretty much done. Collect is a little more interesting, and this is the second method of the Prometheus collector interface. So collect accepts a channel of Prometheus metrics that you can send on, and what we need to do first is take a metric snapshot using our function that we passed in. And this must be concurrency safe. So if you think about it, you might have one Prometheus server, but you could have 2 or 5 or 10. So you need to make sure that you lock appropriately so that nothing can run into like a nasty data race. So we retrieve the value, or if it fails, we can send an invalid metric to notify Prometheus of the error, and we can alert on that later on. But if it succeeds, we take that request value, we use this must new const metric constructor, pass the name of our metric, the fact that it is a counter type, and the raw value of the request. We'll talk about const metrics shortly and why those are important. So if you want to build an exporter in Go, here are my recommendations. Build reusable packages. You don't want to mix low-level details of some file format or binary network protocol or file system traversal with actually exporting metrics. If you separate these things cleanly, you're going to do yourself a lot of favors in the long run. Write unit tests. If you think about it, a Prometheus exporter could be a pretty critical part of your production environment. You need to make sure this thing functions appropriately. So my recommendation is to set it up in tests and perform HTTP GET using some fixed set of inputs and a fixed set of outputs, and compare the two. And finally, use PromTool check metrics for linting your metrics. So what this does is if I curl some exporter and pipe it through this tool, it will give me recommendations on how to make my metrics more standard. So in this case, we have this metric called x gigabytes, and this is a counter. So counters, by convention, should have a total suffix. And also, you'll notice that we use a unit of gigabytes. Instead, you should use the base unit of bytes, and leave that conversion up to your display system, such as Grafana. With that being said, let's go get some metrics. So some of the sources of metrics we're going to talk about today include files, hardware devices, and system calls. And there's definitely some overlap between the three. To start, let's talk about files. In particular, gathering metrics from procstat on Linux. So procstat contains kernel and system statistics. That's a fun one to say. So the numbers indicated here are the amount of time the CPU spent in various states, such as user, system, idle, etc. And these are in a kernel internal unit called user hertz, but you can convert it to seconds later on. So the top line shows us a summary of all these times added together, but we don't need that, so we can skip that. And like I said, for the purposes of our talk, we're going to look at user, system, and idle, even though there are, I believe, 11 different values here. So to start, let's focus on creating a clear and concise exported API. We create this CPU stat structure, and this contains stats for an individual CPU. We give an ID, which is in the string format, so we can have CPU 0, 1, 2, or 3, and etc. And then we export the values that we care about as integers here, user, system, and idle. So next, we're going to create this top-level function, scan. And scan's job is to read and parse CPU stat information from IOReader-R. If you're familiar with Go, IOReader is one of the most fundamental interfaces in the Go standard library. It essentially represents something like a file or a network stream or a byte buffer. And this is great because we can accept a file in our production code, but we can also swap it out for a byte buffer or another source later on for our tests. So use interfaces. They're very powerful. And also, as it turns out, the buff.io scanner type takes an IOReader-R, and we can use that to easily scan over text-based input. So we create this buff.io scanner. We're going to skip the first summarized line because we don't need it, and then we enter this inner scanning loop. If, for some reason, our scanning loop exits early, say, for example, we're reading from a network stream and there's EOF or something similar, we need to be sure we check the error from this scanner type. This is important and often overlooked, so be careful. So within the inner loop, we need to carefully handle our slice boundaries of this file. So within the loop, we have these CPU stat lines. We know that each one should contain a CPU prefix and exactly 11 fields. So we explicitly check for both of those things. If a line doesn't have a CPU prefix, it's not related to CPU stats, and we don't care. But the lines that we do expect, we know they should have 11 fields, so we make sure we check for that, because otherwise, if you access your slice later on, you could run into a nasty out-of-range panic that'll take down your program, and nobody wants that. So now that we've gathered these values into this string slice, we're going to parse the values we care about, user, system, and idle, from indices 1, 3, and 4, respectively. And we're going to parse them into an array of 3 values, because we know exactly how many we need. So we iterate over the indices, we convert the raw string into an integer and pack it into our array. And finally, we unpack it all into a top-level CPU stat structure at the end of our loop. So now that we've put this all together, let's build an example to try out our API and just see how it goes. So we open a handle to procstat. We defer closing it to make sure that we clean up after ourselves, and we pass the file, which is an IO reader, directly to our CPU stat scan function. If it succeeds, we're going to iterate over all of those structures and print them to the screen. And as you'll see, it seems to work just fine. And like I said, all of this code will be available in the slides as well as my talks repository, so check that out later if you'd like to see full examples. So now that we've put this all together, let's build a Prometheus exporter. So to start, we need to wire up our dependencies appropriately in our function main. So we're going to create this stats function. And this is a closure. It has no arguments, and it returns a slice of these CPU stat structures. And within each call to this function, we're going to open a unique handle to procstat, defer closing it to make sure that we clean up, and then pass it to our CPU stat scan function. So this fulfills 2 purposes. 1, every time this function is called by collect or collect, we get a unique handle to procstat, so we're totally concurrency safe. And 2, this is nice because we can swap out this function right here for one that returns, say, a fixed set of values for our unit tests. Makes your life much easier. So we pass this function to our collector type, and then we register it with Prometheus. So this is our collector type. We're going to export a metric called time user hertz total, and we're also going to pass that function explicitly as a dependency of the collector. So here's a tip. When you're working with fields that have, or structures that have repetitive fields, such as user, system, and idle integers, you can use anonymous structures to simplify your code somewhat. So we call our stats function here, we get our stats, and we're going to iterate over each entry, and what we want to do here is we have this slice of anonymous structures. If you've ever done table-driven tests in Go, you may be familiar with this. But essentially, we're going to associate each of these mode strings with the raw value. So the user string is associated with the user value, and so on. Next, we iterate over all these tuples and unpack them, and then we create the metrics using this must-new const metric constructor. And we're going to associate 2 labels, the ID of the CPU and the current CPU mode. So let's talk about const metrics while we're here. Let's say, for example, I have a system with 2 CPUs, and they're hot swappable. So your exporter is running along, you're getting metrics from both CPUs, and suddenly one of the CPUs dies, or you take it out of the system. If you don't use the const metric constructors, the Prometheus client will continue to export the last value for those time series forever. So you need to make sure that if you're implementing the Prometheus collector interface, you use the const metric constructors because they allow time series to come and go as time goes on. All right, let's put this all together and give our exporter a try with curl and just see what happens. So we curl the exporter, we run it, and as we'll see, we have some metrics available with our given labels, such as the CPU ID and the mode, and these raw integer values. So if you want to gather metrics from files with Go, here are my recommendations. Use IO reader whenever possible. This is much more flexible than, say, accepting a file path in your API. The buff.io scanner type is super useful for all the files that reside in proc and sys, because typically these are text files that are pretty easy to parse, and that's a great type for doing so. Always check your slice and array boundaries. You don't want to run into an out-of-range panic in your exporter. It's no fun for anybody. And also, check out the Prometheus procfs library. We've done a lot of the work for you for these types. All right, let's move on to the second part of our talk. So let's gather metrics from some hardware devices. In this case, the Silicon Dust HD Home Run. So who here still pays for cable TV? Wow, just a few of us. I love my cable TV, okay? I love NFL and HBO and all those things, but this is a pretty cool device if you have a cable subscription. I understand it also works with over-the-air, but this one's specific to cable. So you get your cable from your provider, you plug it in, you get a cable card to decrypt the signal, and you plug in an Ethernet cable, and what this becomes is essentially a network TV tuner. So you can use this to watch live TV on different devices, or also record to something like a Plex media server. So they also offer a Linux utility, so I started poking around. And I can discover the device in my network and use its ID to ask it questions, such as give me your tuner debugging information. And as you'll see, there's a lot of different statistics available here. We have information about the tuners, such as the current channel and the channel it's trying to lock to, the signal strength, the signal-to-noise ratio, various bit rates it passed within the device, and finally, the network packets per second and error rates. So naturally, I bust out TCP dump and start looking around at all these packets, but it turns out I didn't ever need to do that because Silicon Dust actually has an open source library called libhthomerun written in C. So we can use that as inspiration to create a Go client. So let's start by building a Go network client API. We create this client type. It has a mutex, so we can serialize access to the device. We're going to embed a connection in there, and we also give it a timeout. If you're making a network connection, add a timeout. Next, we have this dial constructor, and dial's job is to dial a TCP connection to an HD home run device. So first, we need to build up our low-level communications types. The HD home run speaks using these specialized packets. So this is what a packet looks like in Go. A packet has a type that specifies the type of message it carries and tags. And these specify optional attributes such as debugging information or information about the device and lots of other things. So then we create this low-level function called execute. And execute's job is to send a single packet and receive a single packet. So we lock the connections to the device, marshal it to binary format, write it out, wait for a response, unpack it, and then we're all done. And you'll notice I've omitted the error checking, but don't ever do that in production code, ever. On top of that, we can build a higher level friendly API, because who cares about what the packets for this thing look like, right? So we create this high-level function called query, and query's job is to perform a read-only query to retrieve information from the device. We accept this query string, we put it into our packet, and then we send it to the device. And while I'm here, I want to mention this really cool tool called C4Go. Given a C header, you can output pure Go constants, so you don't have to write down enumerations by hand. Super useful if you ever work with anything from the kernel, would recommend. But we can do even better than that query function. So we're going to create this tuner debug type that contains debugging information about a tuner. And then we can add this tuner debug method to our client type. We query for the debugging information from the device for tuner 0, for example. We retrieve this raw byte slice. And hey, as it turns out, a raw byte slice is a lot like a text file. So it's pretty much just the same routine as we did last time. We wrap the byte slice in a bytes reader so it adapts to the IO reader interface. We can put an IO reader into a buff.io scanner, scan through the file, and hey, we're all done. So now let's build an example program and just give this a shot and make sure it all actually works. So I build and run my program, give it the ID of my device, ask it for the tuner 0 debug menu, and as you can see, it seems to work just fine. So let's move on. We want to export HD home run metrics using Prometheus. So how do we do that? Well, the HD home run device has this network API, but we can't actually run our own code on it. It's a lockdown little third-party device. So what we have to do is enable our Prometheus exporter to dial out to a remote device. This is where things get kind of interesting. So we create this function dial, and dial is used to connect to an HD home run device given some address string. It's going to create the HD home run client for us, and within dial, we're going to call our HD home run dial method or function, and then we're going to make sure we set a timeout. You want to always set a timeout on your network communications, because what happens if something goes wrong? The device is down, your network is down, something in the middle is down. You don't want to necessarily leak file descriptors. Otherwise, you run out of file descriptors, your exporter stops working, you get paged. Nobody's happy. Okay, so we have our dial function. We pass it as a dependency to our handler type. And the handler is going to look something like this. So our handler is going to implement the HTTP handler interface from the Go standard library. And we're going to do that now. So this is where this gets interesting. We need to actually configure Prometheus to send a target parameter with each scrape request. So we're going to retrieve the target parameter here. We're going to validate it and make sure it's got a valid port. And if it doesn't, we add the default. We join it back together, and we try dialing out to whatever was passed as the target. If it fails, we return an HTTP 500, so Prometheus can know something is wrong. But if it succeeds, we're going to defer closing the client. We're going to wrap it in a small interface for testing, and we're going to actually serve the metrics for it. So what might that interface look like? As it turns out, our HD home run client can do most of the work for us, actually. So we create this device interface here, and it's going to wrap the HD home run device type, or the client type, and it has the same method signature as our HD home run client. So by the rules of Go, the HD home run client type implements our device interface. So putting this all together, let's give the exporter a try with curl and that target parameter and just see how things go. So we curl our exporter running on, let's say, my local machine, and it dials out to the remote HD home run device. So we expose a couple of metrics here. We have network packets per second that shows the packets per second rate for a given TV tuner. And we also have this interesting tuner info metric. And this contains metadata about each of the tuners available to a device. And it exports a constant value of 1. More on this shortly. So if you want to configure Prometheus to actually use this thing, you have to make Prometheus pass a target parameter. So this configuration is mostly taken from the black box exporter, so definitely look at that repository for more information. But the basic ideas are, you have this targets list, and you pass a list of, like, say, for example, your HD home run devices. You create this relabeling configuration, and this tells Prometheus to pass the target parameter, and also to replace, I believe, the address of the HD home run exporter in the metrics with the address of your HD home run device. So relabeling is a super powerful concept. I definitely recommend reading more about it. Particularly the Robust Perception blog is super useful. Putting this all together, it seems to work just fine. Prometheus is up and running. It is scraping our HD home run exporter running on some machine, which reaches out to our HD home run device itself, gathers the metrics, exports them in Prometheus format, and everything is good. So let's go talk about that information metric again, that metadata. You can use these synthetic information metrics for super powerful PromQL queries. So we construct it like this. We have these labels here that are the tuner, the channel it is trying to lock to, and the channel it's actually locked to. And we're going to export this metric. It has a constant value of 1, it's a gauge, and it just has these labels. So why is this useful? As it turns out, PromQL is super powerful, and you can use this to effectively perform a relational join between different time series. So if I want to answer a question, something like, what is the packets per second rate for a given channel? This query seems to work. So I'm effectively joining my network packets per second query on the channel ID with my HD home run tuner info metric. And as we'll see, on channel 3 for my HD home run device, on tuner 0, the packets per second rate for that channel was 840. So this is another super powerful PromQL concept. And in particular, if you want to learn more about this technique, check out Brian's blog and how to have labels for machine roles. So if you want to gather metrics from hardware devices, here are my tips. Set timeouts for network connections, always. Just do it. It won't take you very much time, just do it. Use interfaces for testing. It makes your life much easier. You shouldn't have to dial out to an actual hardware device to run your unit tests, right? Create these synthetic information metrics. So yeah, you could add these labels to every single one of your Prometheus metrics, but then you could result in some very high cardinality time series, and that's no good for Prometheus. So take advantage of PromQL. Export your labels as metadata on a single metric, and then join them together using PromQL. And finally, learn a little bit about relabeling. It's a super powerful concept, and one I'm admittedly not very familiar with, but it's super useful. And that brings us to the home stretch. So let's talk about gathering metrics from some system calls. In this case, StatFS on Linux. So StatFS is used to get file system statistics. So given some mount point, the function StatFS returns information about a mounted file system. So to start, we want to build a high-level OS-agnostic API, because that's the friendly thing to do in Go. So we create this file system structure. It has a path or mount point, a type, which is an enumeration of file system types like ext4 or NFS or XFS, and the number of files that reside within that file system. We create this top-level function get with a capital G, and this retrieves stats for the file system mounted at path. Within get, we're going to call get with a lowercase g, and this is going to be our operating system-specific implementation of get. So if you want to make use of system calls in Go, you must always guard them with build tags. Your code won't compile on other platforms if you're using system calls unless you're using build tags appropriately. And this is one of Rob Pike's Go proverbs. So let's talk about the Linux implementation first. We have our file statfs_linux.go, and we have this Linux build tag at the top. You don't necessarily need the build tag just because of the file name, but I like to add it just because it's more explicit. And instead of using the standard library syscall package, we're going to use golang.org xsysunix. This is effectively the modern replacement for syscall because syscall had to be frozen after a certain period in time. So get, once again, lowercase g, this is going to be our Linux implementation of that function get. It accepts a path, and then we're going to create this Unix StatFS T structure. We call out to this Unix StatFS system call, provide it some mount point, and we pass a pointer to the structure. And as a result, the kernel is able to populate that structure, so when our function call returns successfully, we have a structure with all the information that we need. Finally, we unpack it into the OS agnostic structure. Remember, system calls can't cross the boundary outside of where your build tag is. So we unpack the structure here within our Linux type to make sure that it's friendly for all operating systems. So next up, we're going to talk about code that's not on Linux. So we have this file, statfs_others.go, and at the top we have a build tag that says, for every operating system that is not Linux, build this code. And here, we're just going to leave the function get unimplemented. Perhaps there are similar APIs for other platforms, but for the time being, leaving it unimplemented is fine. And I typically like to return an error that says something like, whatever this is not implemented on your current platform, such as Windows, Darwin, etc. So next, let's build an example program and give this a shot and just make sure it all works. So we create our program, we call out to it, we get the first argument, and that's going to be our mount point path. We pass it to our statfs get function, and this should compile successfully on all platforms, even if it doesn't run. And then we print the information to the screen. And as you'll see, it seems to work just fine on Linux. Of course, you can implement more platforms if you're able, but for the time being, Linux only is OK. If you want to export metrics for this, well, I'm a little shorter on time than I might have thought, so this is going to be an exercise for the reader. If you want to gather metrics with system calls in Go, here are my recommendations. Build a high-level, easy-to-use API. Your caller should not have to care about system calls or pointers or any of that kind of unsafe things. So make sure that you make it as easy to use as possible and take away as much of the complexity as possible from your caller. Always use build tags with system calls. If you don't, your code will not compile on all platforms. And Go is a great cross-platform language, so we should keep it that way. And also, be really careful about using elevated privileges with system calls. It's pretty easy to do something like, I don't know, overwrite your main disk or reboot your machine or something nasty. So just be cautious about using root. So in conclusion, if you're going to build Prometheus exporters in Go, it mostly comes down to a set of typical software best practices. Avoid global and package level state as much as possible and pass your dependencies explicitly as parameters. It's going to make your life much easier in the long run. It makes your code easier to read, easier for your coworkers to review, and easier to maintain in the future. Focus on creating simple and reusable package APIs when building exporters. Like I said, you don't need to mix the details of exporting metrics with crawling a file system or some binary format or some network protocol. Separate these things, create nice reusable packages, and then import them into your exporter. And finally, read up on the Prometheus metrics best practices from Prometheus.io. These are really great. There's a lot to learn, but apply them judiciously in your exporters, and you'll be better off in the long run. And finally, I have a special unrelated announcement. DigitalOcean is working on a Kubernetes product. So if you're interested, there are some folks in here who work on that, or otherwise, come see us at our booth. And that's it. Thank you very much for your time, and I look forward to answering your questions. All right, well, I'm not sure where we're at on time right now, but I'd be happy to take any questions if anybody has any. Otherwise, just come find me in the hall. That's just fine, too. 7? OK. Sure.
We have a bunch of existing components which want to push metrics and provide multiple formats on a periodic basis. How would you advise best converting that to something Prometheus could?
I'm sorry, I think I missed some of that. Could you speak up a little bit?
So we have a bunch of components which push metrics.
Yes.
And a project on them. How would you best convert that to a full format?
Yeah, so the question was, if you have a bunch of metrics in a push format, how can you best convert that to a pull format? To start, I believe there are lots of Prometheus exporter adapters, essentially, for things like statsd, graphite, et cetera. So if you wanted like a stopgap solution, you could push to those exporters instead, and then those export native Prometheus metrics. But if you want to actually swap it out, it kind of depends on your application. So you might have to go through and, like, I guess I don't know which languages you're using in your environment, but many? Yeah, sure. So it's kind of tough, but yeah, so my recommendation would be definitely look at the adapter exporters, things like the statsd exporter. There are several under the Prometheus organization, so check those out, and those will probably give you a good start. Mm-hmm. Any more? Yeah? OK, nothing? Yeah, any more questions? All right, cool. Thank you very much. Yeah, go ahead, sorry.
How easy do you think it is to and etc. I mean, how easy do you think it is to be deployed in Kubernetes? This is my question.
Sure.
Do you have something prepared, like a YAML file with the best practices? This is the way how you should do it. Afterwards, you do whatever you want.
Yeah, sure. So the question is, how easy is it to deploy Prometheus in a Kubernetes environment? And if so, do you have like YAML files prepared for deploying Prometheus in a Kubernetes environment? And truth be told, I don't deploy Prometheus in Kubernetes. I have coworkers here who do. I'm sure there are folks in the room. I run this at my house using systemd and Ansible. I'm bare metal native, right? But yeah, so unfortunately, I'm not the best person to answer, but I'm sure there are folks here who'd be happy to help. Any more questions? Cool. Thank you very much for attending my talk, and I hope it was entertaining.